let's create some equations and formulas. And in addition to that, we're also going to talk about if you're going to do this well, then you should be able to perform a unit analysis on your equations for everything to work out swimmingly. And really, we generalize formulas and we solve them for specific values. So let's just get started with some solving of equations, which we've done in previous sections, but now we're going to revisit. So we are going to find what x value actually makes this equation true, or this truly equals. So some number gets tripled, then deduct 7 in order to get 15, which means before the deduction has to be what, 22? Because 22 take away 7 is 15. So that must mean that this triple sum value is 22. Okay, so because then we would deduct 17 and get 15. And if we triple some value and it's 22, it must be 22 thirds, because if we take 22 thirds and we triple that, then we have 66 thirds, and that's 22. So, okay, scale down. Okay, and let's see, that means that x is 22 thirds, which is totally fine if you want to leave it like this. 3 sets of 22 thirds is 22. 22 take away 7 really truly does make 15, and then the equals is actually true. How many times does 3 go into 22? 7 times? And there would be 1 left over, so this is really 7 holes. 21 thirds will create 7 holes, and then there would be an additional 1/3 left over. All right, let's solve again. Oh boy. Now it looks like we're going to need to distribute first. So let's triple these things, but opposite and triple. So 3 x's, opposite style. 3 sets of 2 is 6, opposite, so negative 6. And then plus a 5x, got it, is equal to 14. Oh, double a 7 and we get 14 again. And 2 sets of 4 x's, but negative style. So 2 sets of negative 4 x's, that would be negative 8 x's. Okay. On the left side of the equal, I see that we can combine. We are down 3 x's, but then we're back up 5 x's. So overall, we're up 2 x's. And over here, there's no like units with this 8x, but we do have 14 and 14, and those are assumed to have like units. So 14 and 14 makes 28. Okay, so far so good. I'm going to go ahead and add 8 x's to both sides, and I'm going to add 6 to both sides of this. So let's see. Add 6 to both sides, and I'm also going to go ahead and add 8 x's to both sides, and adding the same amount to both sides of the equals maintains the fact that we can still use an equal sign. Perfectly balanced operation here. If I'm going to add some to one side, add the same amount to the other. Well, that means that I'm going to have 10 x's. 2 of them plus 8 of them makes 10 of them. This would go away. Down 6, up 6, 0. 28 plus 6 is what? 34. And down 8 x's, add 8 x's, zeroed out. And then we just need to scale this down. Scale this down by 10. That means x is 3.4. Okay, so if we plug 3.4 into both into each value for x on the left side of the equals, and then we plug in 3.4 on the right side of the equals, these would really end up truly being equal to each other. Okay, let's look at this. An item that originally cost $2,000 depreciates by $25 each year. How much is it worth after 2 years? So first, that's its initial worth. The value of it is the response variable, and it is responding to the explanatory variable of how old it is. And this is the constant amount being subtracted each year. So the constant decrease each year. So actually, what are we saying here? It's originally worth $2,000, depreciates by 25, find its worth after 2 years. Oh, okay. Well, I don't even feel like we need to solve an equation. I feel like we need to take $2,000 and take away, oopsie, white out, 2 25s, or 25 2 times. I'll write it like that. Okay, take away 25 2 times. Got it. Well, that's 50 bucks, so 1,950. How much it's worth after 2 years? 1,950. An item that originally went for $2,000 depreciated by $25 each year. How much is it worth after T years? Well, here's where that 2 was. And remember, if it's a constant rate, a constant subtraction or addition, remember our linear equations had this constant add or subtract each time. And so here what we have is, let's call it worth. Okay, the worth is equal to initially $2,000, but we would take away 25 T times. So take away 25 for each year that passes. Yeah. Okay, so find out, this is how we would find out what it's worth after T years. An item that an item originally was worth $2,000 and depreciates by $25 each year. Find how much time has gone by when it's worth $800. Oh, so this is very similar to the scenario number 4, except now we know that the worth is $800. So right here, we know that is the worth, but we don't know how much time has gone by. Okay, so we're going to put in 800 for the worth. And we know it started at $2,000 and it's going down 25 bucks a year. So how many years does it take? Well, if I look at it like this, I know that 2,000 take away 1,200 is going to give me 800. So I know that 25T has to equal 1,200 bucks. Okay, just because 2,000 take away 1,200 is $800. Now, in order to use proper steps of solving equations, I think what I would have done is subtracted 2,000 from each side, or added 25T and subtracted 800. So it is perfectly acceptable to maybe do this in 2 steps, which would have looked like add 25T to both sides, and then subtract 800 from both sides. Okay, so if you like to do your step-by-step business, that is how I would do that. But really, I just reasoned this out. $2,000 take away 1,200. So that must mean this 25t has to equal 1,200. Oh, scale each down by 25. And that means, oopsie, I get 48 for t. How much time has gone by when it's worth $800? 48 years. It is 48 years old. Yeah? Okay, and a quick recall. So, I'm going to write down this recall, but there's another recall that happened too. So up here, I'm actually going to draw in another recall right here. And that was that the response was the initial plus or minus the constant change times the explanatory variable. So this is actually my first recall, and we just used it. We said 2 grand, take away 25 t times. And then another recall that I want you to remember is that up here, we started combining things like x's with x's and non-x's with non-x's. And that's because I want you to remember that we combine like terms. Or like units. Okay, so for instance, 3 apples plus 8 apples is 11 of them. And I don't know, let's suppose we're going to 8 miles per hour and we increase that by 13 miles an hour, then what is that, 21? Then, I mean, we started at 8, we increased it by 13, now we're going 21 miles per hour. But if we had something like 8 miles plus 13 miles per hour, we would be like, what? Okay, so up here, and here's another one. Let's suppose we had 3 11s plus 8 11s, right? That would make this, oh, crud. I don't want to go with 11. How about, let's make this nicer. 3 10s and 8 10s, then all of a sudden we actually have 11 10s. Yeah? So we can combine like values and we can combine like units. Apples plus apples is more apples. And 3 10s and 8 10s makes 11 10s. And down 3 x's and then add to it 5 x's gives us 2 x's. So remembering that x is just a number or a unit, number or a unit, then we know that we can combine these similarly as like terms or like units. So let's talk about a unit analysis. Yes? And to me, this is using operations on labels or units in order to check for mistakes in an equation. So let's write that down. Using operations on labels, also known as units, hence the name unit analysis. In order to check for mistakes in an equation Okay, in order to check for mistakes in an equation, by the way, I feel like every formula is an equation. So equation, formula, or conversion. But I hesitate to rewrite the word formula because to me that is just another equation. Okay, so, or conversion. So we're really chasing those units around to make sure that we really did convert them accurately. So I do have another quick remark here, and that is this, that some equations and formulas from your past. So first, formulas are equations. Okay, so that's my first quick remark here, but I'm going to tag into that you have seen some of these. So, for instance, I don't know, area is length by width. Here's a formula. And we would just make sure that all of our units, the units on length, what is this, inches by inches to give area in square inches. But if we had inches and liters, we would know there was a problem. Here's another geometric one. Perimeter of a rectangle, 2 L's, 2 W's. Not to mention perimeter and area of a circle, what pi r squared and 2 pi r. We had other ones. So, I don't know, how about the population? I vaguely remember there was a city with a population of 4,000 that was increasing by 30 each year. There's a formula. Okay, still an equation, but it's a formula relating the population to the time past. We had a cost one. The cost is, I'm remembering there was like a $2 flat fee plus $4 per pizza or whatever. $2 plus $4 per pizza, right? And that was the cost of getting, total cost of getting pizza. We just did one with value where it started at, okay, so we just had worth equals $2,000, take away 25T, where it's depreciating by $25 each year. I mean, there's just a lot of formulas and equations that we know, and we're just really talking about what we see all of these we see all of these variables. We just need to keep track of them. Oh, here's another one. That distance is our rate or speed times our time. So I don't know, we're going 30 miles an hour for 2 hours, then we've gone a total distance of 70 miles. But notice that in order to think about this formula or this equation, I really was thinking about the units. I thought about our rate as a speed, and speed are miles per hour sometimes, and our time is in hours. So I was really thinking about the units in order to check for the mistakes in this particular formula. In example 2, we're going to perform a unit analysis to see if these really make sense. All right, let's do that. Suppose y is equal to 10x plus 9. So where 10 is in dollars, x is in hours, and 9 is in dollars per hour. Does this make sense? Okay, let's see. Well, we would go $10, okay, times X number of hours. So we would have dollar hours here, plus $9 per hour. I do not see these as like units. These are dollar hours and these are dollars per hour. Those are two very different things. Not like units or common units. They're just not in common. So now let's suppose we have the same equation where 9 is in dollars, X is in hours, and 10 is in dollars per hour. Okay, so now let's retry this and see what we get. So $10 per hour, and then times X is measured in hours, X hours, and then add to that $9. Okay, so now all of a sudden this will make sense. If we are working and we're getting paid $10 an hour and we work for 3 hours, then this turns into $30 and the hours are gone, right? It just turns into whatever we multiplied and then in dollars. So if this is $30, $30 plus $9 is $39. So this is dollars plus dollars. So I'm going to write this. Where Y. So this does work out, and if you combine dollars with dollars, you get dollars. So this one we can add dollars plus more dollars and get more dollars out. So these really do work out. These units, they end up being in common. Okay. Let's see. An item that originally went for $2,000 depreciated by $25 each year. Show how much it's worth. Okay, so we already wrote an equation for this. I'm going to rewrite it down. W equals $2,000 minus 25T. Then check to make sure the units are combining like terms. Okay, this 2,000 is in dollars. Okay, this 25 is in dollars per year. And notice how I'm replacing every number and every variable with a label or a unit, and I'm leaving the operations. So this is dollars, and then minus 25 is in dollars per year, and then times, time in this case is in years. So this would be dollars, take away dollars to find the worth in dollars. Okay, so this actually does work out too, where W is in dollars. So this one works out as well. And that means the equation we wrote is accurate because we had dollars take away dollars, and so we're good to go. The model H of T equals 22 minus 3T kept track of hate crimes since the year 2006. Okay. I have no idea what's happening right now because of the pandemic, total chaos. So I can't even say what's going on with this. I can say that it would be interesting. It would be interesting to track this with the real FBI database to see what's been happening more recently. Anyway, write the units for each number. Okay, so here's our model. And write the units for each number and variable in this equation to make sure it makes sense. Okay, so it looks like it's been going down. it says that this is since the year 2016. So immediately I can write that T is years. I'm sorry, 2006. Since 2006. That's kind of hopeful. I like that. And then, so we know what T is, but now we don't know what are the units on 22, and we don't know what are the units on 3. Okay, but I do know that the 22 is an initial amount, and we're keeping track of hate crimes. So the units on the 22 is 22 hate crimes. Yeah, so that's its label or its unit. And the label on the 3 is how much it is consistently going up or down, and it's going down by 3 each year. What's going down by 3 each year? The number of hate crimes. So this is 3 hate crimes per year, right? And you can attach the negative. You're like, well, it's going down because look, it's being subtracted. But did we do that? And H, so last H is measured in number of hate crimes. Okay, so what that means is that if we take 22 hate crimes, take away, you know what, I'm just going to write it instead of say it, right? So we have the 22 is hate crimes, take away 3 hate crimes per year times the number of years. Then we have hate crimes, take away hate crimes is fewer number of hate crimes. Yay! Okay, I really want to check it. This is a hopeful example here. Okay, but each one of these numbers and variables deserves its tag. Like, what is this representing? This 22, what does it represent? Is it 22 apples? No, that's 22 hate crimes. Okay? In the next video, we'll go ahead and we will solve a problem, and we will again, so in these two we created our linear equation because we had taken some situations and we had generalized it into the initial value, take away the constant amount of change each time, right, or each whatever, however many times. So we generalized to create a linear equation, and now we're going to try to solve a problem and generalize that to create an accurate formula or equation for that situation. So let's try generalizing again.